Spend enough time staring at the sky, you're gonna notice something weird. Almost all of the stars move together, but a few of them, indeed some of the brightest of them, wander on their own paths. These points of light, which we named Mercury, Mars, Venus, Jupiter, and Saturn, are all very clearly acting strange. And for a long time, that's what planets were. A point of light in the sky moving differently from all the other points of light. And that definition was fine. It was useful, a description of what we saw going on. But you were raised in a world of 8 planets, or 9, depending on when you were born. The 5 that we always knew were up there, plus a couple more that we couldn't see, and also plus Earth. And this is also fine. Like the definition of a planet that includes Pluto and also probably Ceres and Makemake and Eris and a bunch of others, that's fine. We're looking for utility here. We want people to have a starting point from which to build their fuller understanding of the solar system. But if you memorize the names of the planets and stopped there, if you got my very educated mother just served us noodles, and that's that, you're not being well served by the rubric. That was a first step. There are more steps to take, and we're gonna take one today. The 8 planets frame encourages you to imagine the solar system as a set number of important objects that you know the names of, and then an uncountable number of unimportant objects that you could safely ignore. There's the planets, and then there's all the nothing stuff. There's the moons and the asteroids and the comets. And this is why we got mad when Pluto got demoted, because we think if it's not a planet, it must be nothing. You are not being well served by understanding the solar system in this way. You are missing some of the most important stuff. One of the ways my brain has shifted as I have thankfully learned more about the solar system and how it actually works is that some planets are not primarily planets. I mean, they are planets. There's a planet in there, but they're also more than that. Like Venus is just a planet. Mars is just a world with a couple of bumpy rocks orbiting it. That's a planet. Saturn, though, is something else. It is something weird and messy and confusing and mysterious, full of mysteries that are not just about the one object that is that ball of gas. It's about interactions between many objects. Saturn, like the solar system, is a system. Now, I know that I've titled this video somewhat controversially, that Saturn isn't a planet. And that's like saying that the sun isn't a star. But I do not primarily imagine the important part of the sun being that it is a star. I imagine the important part being that it is a solar system. And in the same way, the most important thing about Saturn is not that it is a planet, it is that it is a system of worlds. Now, compared with Jupiter's 4 massive worlds, the Saturn system might seem a little lackluster, but no set that contains those rings or Titan could possibly be boring. Titan is probably the most interesting world in the solar system that isn't Earth, and I'm counting all of the other planets. So I want to give you a little bit of detail about the Saturn system, and that's going to include me talking quite a bit about Titan and also talking to a scientist about a mission that is going to Titan and about the bizarre chemistry of Titan. But first, I'm going to hit you with a little bit of history. All right, 1671. Around 60 years after Galileo first spotted some of Jupiter's moons, Giovanni Cassini had a better telescope. It was 60 years better. Still not great, but good enough to see some moons of Saturn, including Iapetus. And Iapetus was not acting normal. All the moons that we had discovered before this time did a very mathematically normal thing. They spent some time on one side of the planet, and then they moved over to the other side of the planet, and then they moved back. And this makes sense once you understand that they are worlds orbiting worlds. What would not make any sense at all is if this little point of light showed up on one side of the planet, and then when it should have moved to the other, it was just gone. And this is what was happening with the Iapetus. When it was on one side of Saturn, it was there and you could see it, and then it would go to the other side and it just wouldn't be there, and then it would show back up on the other side visible again. This is very weird. Was Galileo wrong? Were these not worlds orbiting worlds? What was going on? Well, Cassini came up with a potential explanation. He had a hypothesis. What if one side of this moon were bright and shiny and the other side was dark and absorbent? So that moon wasn't not there when it was on one side of the planet. It just wasn't reflecting enough sunlight to be visible. And that turns out to be exactly the right guess. These images you are seeing right now were taken more than 300 years later by Cassini. The spacecraft, not the guy, which I love. You know, first the guy's like, what's going on? And then 300 years later, there's a spacecraft with the same name. And it's like, here, you could see. Now, before that spacecraft got there, we had figured this out. But to actually see the dust accumulated on one side of Iapetus is wild. And we actually now know basically how this happened. Iapetus is tidally locked to Saturn. So one side is always facing Saturn, and one side is always facing the direction it's moving in, and one side is always facing away from the direction it's moving in. And there are some moons in the Saturn system that produce some dust, and Iapetus goes through that dust and it collects more on the side in the direction it's moving. Once that starts up, that side then warms up more because it's collecting energy from the sun, because it's absorbing more of that solar energy. So the ice there would sublime away, and then some of that would then recondense on the other brighter side, which would reflect away more of the sun's heat and thus stay colder and brighter. So there's a little feedback loop there that Cassini did not guess at, but he did make the absurdly correct guess that one side was dark and the other side was bright, and that's why he couldn't see it when it was on one side of Saturn. Everything we know is something we figured out. Now, there might be a chance that you are surprised to hear that Iapetus is icy. You should not be. The ring, made of ice, all of these moons that I'm going to talk about in this video are all icy. They're all primarily water ice on the surface. They're not just water ice. There's other stuff going on, especially on Titan, which we will get to. But every moon we're talking about in this video is an ice moon, and some of them are going to be more than just solid ice. Some will also be liquid water, like, for example, Enceladus, which is literally spewing water from a subsurface ocean into outer space. And yes, I don't know if you've spotted it, but I did have Casey, who did the Jupiter moon shirt, do a Saturn moon shirt, and this is Enceladus spewing out the bottom. It spews out the bottom. That's where the spew comes from. And we're going to talk about Mimas soon. That's a weird one, and we're going to talk about Titan as well. We're doing pre-orders for the shirt. You could get it at the link in the description for the next 2 weeks. You pre-order, and then we order the exact amount that get ordered. And that's how that works. So you can celebrate Saturn as not just Saturn, but also the Saturn system. Okay. Importantly, it is much easier to sample water in outer space than it would be to like go to a subsurface ocean below miles of ice. So we can sample the interior of Enceladus because it is putting that interior into space with giant ice volcanoes. In fact, we have already done it, though we didn't know we were going to. When we sent Cassini, the spacecraft, not the guy, to Saturn, we did not know that Enceladus had an ocean. We did not know that it had these geysers spewing water out into space. We knew that there were icy worlds. There were lots of icy worlds. We thought they were all going to be fairly boring. Enceladus is super small. It's about 500 kilometers across. It's a little guy, and planetary scientists thought it was unlikely that it would have held onto enough heat to have liquid water inside, let alone volcanoes of water. So Cassini did not expect to be sampling water ice that had been shot out of volcanoes from the surface of Enceladus. But once it was there and it saw that it could, mission scientists figured out how to get those samples. And they were able to tell a lot of things about these ice grains. They contained more than just water, for example. They contained salts, which indicates that Enceladus's subsurface ocean isn't just liquid, it is also in contact with rock. Now, it could have been possible that the water was just a pocket of water between layers of ice. And that on its own does not allow for much interesting chemistry. But water in contact with rock, hot rock even, that can lead to some really interesting stuff. So they kept on sampling, and Cassini found organic compounds and silica particles that look like they formed in hot water interacting with rock. So now we're talking about the ingredients for life being present and a good chance of ongoing active hydrothermal interactions. None of that means that there are charismatic sea monsters under the surface of Enceladus, but it does mean that Enceladus, as well as other icy moons that almost certainly have warm subsurface oceans beneath the ice, are the best candidates for life in the solar system that we have. They're there, they're worlds, they're doing it. ESA, the European Space Agency, has labeled Enceladus as a high priority target, so there will likely be a mission going there sometime in my lifetime, probably not launching until the 2040s. I'm not getting too excited about it yet. Unlike how I am feeling about Titan, which we will get to, because that mission is happening much sooner. But first, you know what moon people would pretty much entirely ignore if it were a planet? Mimas. They would ignore Mimas. Nobody would think about Mimas. Nobody does think about Mimas. People only ever think about Mimas because it looks a little like the Death Star, which is great. We love a thing that looks like a thing. But in a video where I could have talked about a bunch of different moons, I have chosen to talk about Mimas because there's something weird going on with this boring, dead, icy moon. It is a very big, active mystery for people who study the Saturn system. It seems like something very weird is going on with Mimas, and I want to get into it real quick before we get to Titan. So scientists have mostly used Mimas as a kind of control moon. Like, what would an ice moon look like if nothing had happened to it since the beginning of the solar system? But then, some scientists started digging into Cassini data on Mimas, and they saw something weird in the way that it wobbles. So Mimas, like Iapetus, is tidally locked, so the same face is always facing Saturn, but there's a little play in that, and it wiggles back and forth a little bit. That wiggle can tell you about what's inside the moon. And in 2014, researchers published data showing that Mimas was wobbling about twice as much as it should be. And that could be explained by two different things. One, maybe its core was weirdly shaped. The other option was a subsurface ocean, which wouldn't make any sense. This is an old, dead moon. It shows none of the remodeling that we see with Enceladus. It's basically got every crater that it could have, given nothing on the surface of it changing since the beginning of the solar system. But people kept digging, and in 2024, a paper was published looking at tiny changes in Mimas's orbit, and it really does seem like the best explanation for this would be a subsurface ocean. And that doesn't make sense. And what else doesn't make sense is if you look at the researchers' second conclusion, which is that this ocean is probably less than 25 million years old. And if that sounds like a long time to you, it is not. Like, compress the lifetime of the solar system into a year, Mimas's ocean, if this is true, would have appeared sometime in the last couple days. What? Why? Is there something going on with the Saturn system? Could Mimas be in the process of becoming an Enceladus? What triggered this? How dynamic is the Saturn system? Is it still changing? Is an ocean world younger than monkeys currently being born? I don't know, man. This Mimas paper is pretty new, so we don't have anything like as much data as we would like to have, but it is one among several hints that the Saturn system may be more dynamic than anyone would expect. We're going to talk about that with our guest at the end of this episode. I actually re-recorded this so that the beginning would be shorter so we could get to her sooner because it was such a good conversation. But now, we're going to talk about the crown jewel, not just of the Saturn system, but possibly of the solar system. A real weirdo, an absolute delight. Bigger than Mercury, clouds, rain, rivers, lakes of liquid hydrocarbons flowing across a surface made entirely of ice. Everybody, it's the solar system's most bizarre and otherworldly chemistry experiment, Titan. Titan is, to me, the clearest evidence that the word moon is doing harm to our ability to appreciate the solar system. If this guy were a planet, we would talk about Titan all the time. Titan's atmosphere is thick. It is thicker than the Earth's atmosphere, which makes it also much thicker than any other moon in the solar system. It is, however, extremely cold, averaging around 290 degrees Fahrenheit. That's not cold. Negative, I imagine, is what I should have written. So yeah, no liquid water on the surface, but there is liquid something. Titan has tons of ethane and methane in clouds, in lakes, in rivers, and it also has a lot of energetic particles from space that can inspire those simple carbon-based compounds to do all kinds of extremely weird chemistry, which is what we are about to hear about from our guest, who studies that weird chemistry. Titan is fascinating to me. Like, it isn't Earth-like because it has conditions like Earth. It's Earth-like because these things, atmospheres, wind, rain, clouds, rivers, they're properties of the universe. Gravity still makes rivers flow downhill no matter what the rivers are made of. Rivers still carve the kinds of channels that they carve on Earth, even if they are made of billions of gallons of liquid methane. But the thing about having a bunch of water ice is that in certain situations, that ice can become liquid. And then you have all that weird organic chemistry of Titan's surface getting mixed with the liquid water that we know is so important to complex chemistry and to life as we understand it. And this can happen specifically when a large object hits Titan. The impactor is going to melt some of that ice, and then a crust will form on top, and the liquid can persist under that for a long time, like tens of thousands of years. Now, as for whether Titan, like Enceladus, has a global subsurface ocean, Maybe. Having read about this a little bit, I'm going to stay well out of it because it seems as if the planetary scientists are not currently in agreement with each other. Needless to say, though, an enticing target, which is why we went there in 2005, which is how we got these pictures, and why we are going back. This time with a flying nuclear-powered laboratory, for real. It's like an octocopter that can land in places, do chemistry, and then fly somewhere else. This is extremely cool. It's gonna be like 8 years before we get there. That's a while. But it's soon enough that it's time to start getting excited about Dragonfly. Now, of course, this doesn't mean that Titan is a living world. It is extremely cold. Whatever happens there happens very slowly, but there are people who have seriously considered whether something truly alien could live in Titan's methane. We have no evidence that it does. We know so little about this crazy chemistry oddity. And what Titan might also help us do is investigate the chemistry that comes before life. You probably don't think much about how significantly life has altered the Earth's geology. But Earth's geology is like very altered. A huge percentage of minerals that we have would not be possible without life because they form in the presence of abundant, stable amounts of reactive oxygen molecules, which is a life phenomenon. On Earth, life has been here for so long that it has eaten or altered almost everything that came before it. We do not have anything like a clean sample of the chemical world from which biology emerged. Titan may preserve whole landscapes full of weird, complicated organic chemistry without life having spent billions of years scrambling up the evidence. Now, Dragonfly is not a mission intended to discover signs of life, but it is capable of detecting signs of life, and it's certainly capable of looking at various signs of habitability. But why? Why would I talk to you about this by myself when I could actually discuss it with one of the mission scientists working on Dragonfly and one of the leading exochemists in the world? Sarah Hörst, thank you so much for coming to talk with me about Titan and Dragonfly and the solar system and the universe. I want to start out with a easy one. So you study chemistry and the weird chemistry that happens outside of Earth, which we're just really not used to. It surprises us all the time. Do you think that there's a clean, definite line between living and non-living?
No.
I knew it.
Not even a little bit. We don't have a clean line for that on Earth, right? There's this whole, is a virus alive? Is it not alive? Thing. Viruses are clearly doing a bunch of stuff that if we saw it in any other context, we would be like, that's alive. So if we can't do it on Earth where we have all of the information, trying to do it chemically on another planet, no. I have colleagues who will disagree, but they're wrong.
Okay, I like that you understand your disagreement, not in terms of there's a room for a lot of opinions, but in fact your own certainty of correctness, which I appreciate. So does that then make it difficult to be thinking about how we discover life on other planets?
Yes.
How do you figure out the difference between weird chemistry, which Titan will no doubt have gobs and gobs of, and life?
I have no idea. I literally don't know. And there's people who spend a lot of time thinking about that, people who are much smarter than me, and they spend a really lot of time thinking about how would you make DNA out of a completely different set of molecules, an information containing molecule. And for me, where I come from and the kinds of science I'm interested in, I am just really curious about what the universe does and what it's made out of. I'm not trying to impose, is there life or not on it? I just want to understand what it's doing. And if the answer is, oh, I'm doing life, phenomenal, great, we'll all go collect our Nobel Prize. But if that's not what it's doing, I don't necessarily find it any less interesting, because understanding how the universe works is fundamental to finding life elsewhere.
I hear you, and also I think that is the correct frame to be seeing this inside of. Of course, it's not the frame that I expect the average consumer of pop science news to be coming at it from, but to sort of start from a place of, if you're going to be looking for something specific, you're going to be disappointed. We only have ever done chemistry on one planet, and also yes, sometimes in a space station that's just that planet but without gravity. To have your eyes open to that, it's so exciting. It's going to be so weird. Right. So one of the things that I think, correct me if I'm wrong, but was a big moment for you scientifically was creating some Titan on Earth and finding out what came out the other side. And I was wondering if you could help me with the terminology thing, which I have seen differently in different places. Is there a thing called Tholin Or are there things called tholins?
This is like I wish that we had our linguistic colleagues around to tell me what the correct answer is. I use it in the singular all the time, although I have colleagues who use it in the plural. In either case, it does exist.
Good. That's a great place to start.
So we're on the same team. It was a word that was made up by Carl Sagan and his colleague Bishan Kare many, many years ago. They wrote a paper in the late, I think, 1970s, coining this term. It just kind of means like you took some gases or some ices and you put energy into them and they did chemistry and you made stuff and we don't know what to call that stuff. And so we're going to call it tholin.
So tholin is.
It is.
Yeah.
To be or not to be, it just is.
And tholin is, from my understanding, sort of like a film or like a sticky stuff that happens when ultraviolet light and like stuff from the sun hits organic molecules in the absence of life.
Yeah.
And in like cold, particularly like cold places.
Sure, I guess. Well, that's an interesting question.
We actually don't know.
I don't. Carl Sagan's not here anymore,
Right.
and neither is Bishan Kare, and they were the ones that coined the term, and I have so many questions for them. I would love to know their opinion on a lot of things that are happening right now. We do these experiments just like the ones that we do for Titan. We do for exoplanets now, and we run them up to 800 Kelvin, and that is certainly not cold unless you study exoplanets. And so I think the cold is not necessarily the case. The fundamental characteristic is you are taking very simple molecules, the kind of fundamental molecules of an atmosphere or an icy surface on a satellite, and you're putting energy into them and finding out what happens. And the short answer is chemistry happens and makes a bunch of stuff. And the longer answer is what gets made depends on what you started with, what temperature you're at, what kind of energy you put into it, and then, interestingly, how you look for the answer.
Yeah.
So what kinds of instrumental techniques you're using in the laboratory to try to understand what it is that you've made, because a thing that we know is that there's tens of thousands of different kinds of molecules in there. If you look for something, you will find it. We played this game back when Twitter was a place that some of us hung out. We would play a game where people would be like, is this molecule in tholin?
Right.
And I would be like,
yes.
Yes. And it was like, this was kind of when like Breaking Bad was a thing, and people were like, is there methamphetamine in your tholin? And I was like, did you know?
No.
Well, the molecular formula of methamphetamine is in my tholin. I don't think I made methamphetamine.
Yeah. I have made meth in the lab, but not the way that sounds. You couldn't.
It wasn't on purpose.
It would not go well for you if you tried to smoke it. I can tell you that.
This is the moment that the Dragonfly comms people are like, did we really let her go talk to him?
Yeah, but so is like the banana smell. You know, like it's all in there. Yeah.
No, exactly. I mean, it's all in there. Caffeine, like, and that was kind of the game on Twitter was like, can we stump Sarah? Can we come up with a molecule made of these atoms that she cannot find in her mass spec data? And I don't think anyone ever managed to. Yeah. The stuff is very complicated.
Right. And so there's tholin, and then unpleasantly there's also like you could imagine different tholins given different circumstances. But then sometimes I also see people referring to tholins as the molecules inside of tholin, which I'm like, that's a totally different thing. Actually, that's just all organic chemistry.
It's not great. It's not a good situation that we've made for ourselves.
I'm glad that I found a sore spot. I didn't realize that. I thought that there was going to be an easy answer. Titan is. I am making this video about Saturn. I made a shirt about. Can I send your lab shirts?
Yeah, 1,000%.
Okay, great. Just give me names and shirt sizes, and I'll send you a bunch.
Okay, we will be very excited about that.
The video argues that Saturn is not a planet; it is a system, and we should think of the gas giants as systems more than we should think of them as planets. Because when we think of them as planets, we miss their most interesting parts, which are their moons, which are not really moons. The way that we think of moons, they are worlds, especially the ones that are round. And then Titan is in particular a world, larger diameter than Mercury, and it's got rain. so like that's pretty interesting. And I in that video, I sort of lead up to the fact that Titan is kind of the coolest thing in the solar system outside of Earth.
I mean, obviously.
As a chemist, so that's my background is biochemistry, and it's sort of hard not to feel that way because the chemistry that's going on there. And you just alluded to the fact that you're affiliated with and connected with the Dragonfly mission, which is gonna go to Titan, which is going to be like the coolest planetary science we've ever done. And yes. Anything we could do to speed it up is great. What are you most excited about Dragonfly for?
I have two answers. The first answer comes from me wearing my scientist hat, and so I put my scientist hat on, and the thing that I am most excited about are the data that are going to come down from DRAMS, which stands for Dragonfly Mass Spectrometer. It's the most capable mass spectrometer that we have ever flown to space, and it was specifically designed to help us answer a bunch of the questions that we have had since analyzing all of the amazing data from the Cassini spacecraft that really tell us that Titan has the most complex organic chemistry happening in the solar system, hands down, besides Earth. And Earth chemistry is complicated because of life, right? Scientifically, those are the data that I am the most interested in. As a human being, and I think it's important to remember that NASA missions or any space missions are fundamentally a human endeavor. They're designed by humans to answer very human questions. They're built by human hands. And as a human, one of the things that I am the most excited about are going to be the images from Dragon Cam, which is our suite of cameras on the spacecraft, because we have very little imaging data of the surface because of Titan's thick atmosphere, which is one of the things that is the most interesting about it. We don't really know a lot about what the surface looks like. And when we sent the Huygens probe to the surface in 2005, we were in one little spot. We were using cameras that were built in the early 1990s. I hear the kids these days call that the 1900s. So the cameras were built in the 1900s. And I'm really excited. Like, what does Titan look like? Because, like you said, it rains there, and so many things that I think we just have such a fundamental association with as being Earth-like and Earth-like only happen on Titan. And I want to know what that looks like. And I don't want it to be from a camera that was built in the 1900s.
The 1900s. That hurts. One of the things that is kind of can be hard to get across, or maybe not. Maybe it's just like it's government and there's bureaucracy and we're trying to make the most out of every dollar. But it is so important that we have these images. I James Webb Space Telescope launched with these 4 or 5 just absolutely mind-blowing images. And since then, they've released another 5. And the rest of it is raw data that you have to be, a cosmologist to appreciate. And I'm like, give me one a month. Just give me one a month. I could make a whole YouTube series out of this. People would care. And I was just talking to Commander Reed Weissman from the Artemis mission that they almost didn't have an onboard camera live stream, that was a last-minute hack. And I'm just like, you got to be thinking about the ways that we can help people understand and appreciate and connect with this stuff.
I mean, Juno almost didn't have Juno cameras.
I know.
It bums me out that it's so hard to get the public excited about mass spec data, because I think it's so cool.
Yeah.
But
we'll get there.
It's a two-piece thing for me, right? The images are always going to have the visceral impact, which is why I like to point out that I am also excited about those. The mass spec data, that's part of my job. Part of my job is to be able to communicate with whoever I meet on an airplane, at a school, whoever, and explain to them why the data are so exciting and important. And so I really think it's important to have both of those pieces, because the public gets really excited to look at the raw image data that's coming down. People go look at the data from Curiosity and Perseverance every time it downloads, and there doesn't need to be a NASA press release. There's a whole community that has built up around being excited about those data, and we're excited to have a community build up in the same way around the Dragonfly data. So I think that, we can have both, and it pushes different parts of your brain and your heart. So
you've spent a lot of time creating Titan inside of a box on Earth. What do you think you're getting the most wrong?
That's a great question. I think the thing we get the most wrong is scale, spatial. So, how big our box is. So our box is a 2-liter bottle of soda, basically, is our physical scale there, but also time. right? So when we run an experiment in my lab, we run the experiment for like 3 days. Presumably Titan has been running this giant chemistry experiment for 4.5 billion years. And like my grad students do not want to be in grad school for that long. So we have to change our time scale. But that is something that's really fundamental, especially when you're thinking about origin and evolution of life questions. The time scales that we have in the lab are probably not conducive to catching some of the important processes. And I think that's one of the biggest problems we have.
Totally. And there's, there's different environments on Titan. There's different, there's like, just like there is on Earth, there's cold spots and hot spots. It's all cold, but there's colder spots and hotter spots. And these things all move around. Like when you say that the atmosphere of Titan is hard to see through, it's not just that there's like a thick atmosphere of gases. There's like particles in those gases being blown around.
Right. So we have the hazes that are like the stuff we make in the lab, tholins, but Titan also has clouds. It has convective clouds. Like we're actually having some in Baltimore today. It looks like it's about to rain with, like thunderstorms, although we haven't seen thunder and lightning on Titan yet. But Titan has like, I think at least 5 or 6 different kind of flavors of clouds. So there's methane, there's ethane, there's benzene, there's hydrogen cyanide. So
everybody don't go. Just
I always joke
the last place people will go in the solar system.
Well, there is actually a Humans to Titan movement, which I find, I'm not going to lie, it's led by some of my very favorite colleagues, and I find it mildly perplexing. But yeah, so Titan has this interesting thing on Earth. Our clouds are different because of physical processes. And on Titan, we have clouds that are different both because of physical processes and also because of chemistry. And so they're
made of different things.
Yeah, exactly.
It's so cool.
I'm so glad you like Titan so much. It makes me really happy.
Well, I mean, I guess that's how Jupiter is. Like, it has a bunch of like clouds that are made of different things. Hydrocarbon chemistry, lots of different things, doing different things, interacting in different ways, getting hit by high energy particles. Super weird. And so you have like these tholin hazes, and you also have it on the surface. And then, this is another thing I talk about in the video, we have this potential that there was an impactor not that long ago that would have if there is a subsurface ocean, which I'll give you time to comment on if you'd like to.
I'm going to go hide under my desk now.
Then it may be that you could have that surface weirdness interact with the water weirdness underneath.
I mean, so we know, regardless of whether or not the ocean exists or is involved, we know from a lot of modeling that has been done that when there is a large impact on Titan's surface, we will have liquid water present for tens of thousands of years. And that's one of the reasons that Dragonfly is going to Selk Crater. Like, we want to go to a place where...
How does it stay liquid for that long? Just holding on to the heat of the impact?
Yeah, well, so basically, it's like, well, you're from Montana, right? Or that's where you are
correct.
now? I'm also from Montana. I don't know if you knew that.
Oh my God. Where are you
Great
from?
Falls.
Okay.
Yeah.
Amazing.
Okay, so you know this, right? Like when it gets cold, water freezes. That's like kind of one of its really fundamental things that it does. And when it freezes, it floats, unlike most other things.
Gotcha.
And so what happens is that the top of the impact melt pool flash freezes, and that insulates the liquid water below, allowing the liquid water to stay liquid for, it depends on the composition and those kinds of things, but, on the order of tens of thousands of years.
Gotcha.
Any of the chemistry that is going to happen between the haze particles and the liquid water will have finished in 10,000 years. So that's why we want to go somewhere like Selk. Well, we're going to Selk. That's why. That's one of the reasons why we chose Selk, is that we wanted a place where liquid water has been in contact with the material that was made in the atmosphere to see what happens. And so that kind of makes it so that it doesn't, not that it doesn't matter, but for our question, it doesn't necessarily matter whether or not the ocean is in contact with the surface, because we have this other way in which liquid water interacts with the organic chemistry.
So you were just talking about how when you look at tholin, you find everything anyway. And this keeps kind of happening. Like in the course of my life, we keep finding amino acids and glycine, and we find like specific things, on comets, where you're like, really? A comet? That's not a good place for chemistry, really. It started to make me feel like maybe these like molecules of life in quotation marks aren't that important. That it's just sort of like it's an interesting category of molecules, but they're not going to end up being rare.
do you want me to go down this rabbit hole? So I don't think they're rare. I think it's actually probably important that they aren't rare. So one of the analogies I always tell people is like, people always want to talk about like silicon-based life or this or that and the other thing. And I'm like, if you found yourself in the wilderness and you needed to build shelter and you needed to find food and you wouldn't try to go find like the most rare thing around, right? Like if you're in a forest, you're going to build your house out of like tree branches that have fallen. If you're in, you know, Montana or Alaska or something, you're going to look for fish and berries. Like you're going to choose materials that are easily accessible and abundant to you because you don't want the beginning steps to be hard. Because a lot of the steps later on are going to be really hard, right? And so I don't think it's necessarily any kind of information one way or another that we find amino acids everywhere.
I think it might be information in one direction. Sorry, I hate interrupting people who know way more than me about something. But information in the direction of the kind of life that we have might be a common way for it to go. We find a lot of these weird, complex molecules, and not because they were manufactured by life.
I think one of the things that's most interesting, and it's definitely one of the things that we see a lot in the lab, is that like one of my questions, and it's a big question in the origin of life community, is like, why did life on Earth choose the particular set of amino acids that it chose? So when you see
there are others.
Exactly. And so when you see, for example, people talking about, oh, we found all these amino acids and nucleobases on a comet or in Sarah's experiment or in these hydrothermal vent experiments or whatever, what the press release is not telling you most of the time is that they also found 30 or 40 other amino acids that life on Earth does not use.
Yeah,
and so in this soup of stuff, there were a ton of options. Why did life only use those ones? And what does that tell us about how it originated? And so, like, that's one of my questions is, like, I can give you whatever molecules you want on Titan. I feel pretty confident that Titan is making all of them. The question is, which ones actually matter? Is that a good question? I don't know. We're not going to know until we find something that's going to help us, you know, further along the path.
My friend Joe Hansen would say the answer, Sarah, is the ribosome. That's why it chose 20, and we got the 20 that it chose. Ribosomes happened, and that we locked in.
There are certainly people who are on that team. I am.
Oh, you have a different opinion.
No, I am agnostic in this fight.
Okay, unlike some other.
I'm earlier in the process.
Right. Are you also agnostic on the there is a liquid ocean under the surface of Titan somewhere fight?
Oh, I am.
We don't have to talk about it if you don't want to.
No, it's fine. I don't.
I don't know how hot it is.
So we've had, as you can probably imagine, some like really instructive and I think like useful conversations within the team about these new results that have been coming out for people who aren't familiar. We thought there was one for a long time. Some recent data says, or some recent reanalysis and model results say no.
Yeah.
And I think the answer fundamentally with so many things with Titan is just that the data support multiple answers within the things that we know and our modeling constraints and stuff like that. And so I think that it, for many reasons, would absolutely make sense for Titan to have a liquid water ocean. I think there are other arguments to be made that it doesn't. We know that it has, at the very least, a squishy conducting layer. Whether that's like liquid or like a 7-Eleven Slurpee, and like would TSA consider it to be a liquid? Do you know what I mean?
Can you take it on a plane? That's my definition. Can you take it on
a plane? I am fairly confident if you were able to go down there and sample whatever this is that we're seeing in the data, TSA would not let you take it on a plane.
Whether
that means it's an ocean or not, I don't think TSA would let you take it on an airplane.
Right. I mean, it's important to note that we're just like sucking the like Cassini dry here. We're just like okay, we got this data. I don't know, however many years ago, and we're trying to figure out everything we can from it. And one of the things I talk about, and I don't know if you've followed this at all, is the recent Mimas results where it's like, oh, is there like a very young ocean in a Saturn moon? That like very young, like upsettingly young, which makes me feel that the Saturn system is just like more dynamic than maybe we would give it credit for a thing that's been sort of just doing physics for 4 billion years.
There's this whole like disconcerting discussion about whether or not maybe Titan is like less than 1 billion years old.
Wait, what? All right. Well, I didn't see that paper, Sarah.
I'm so sorry.
What, the planet, the moon,
yeah.
the object itself.
Yeah.
How?
A great question.
It just like jumped. It just jumped off of Saturn. The aliens built it.
So, I don't think it necessarily. It's never alien think. I'm so sorry.
So, have you seen my video? That's called It's Never Aliens.
It's literally never aliens. So you had made the argument kind of when we started talking about how you feel like the giant planet systems are something kind of fundamentally other than just like a planet or a moon or whatever.
We should consider them to be a separate thing.
They're doing their own thing. Saturn and Jupiter have a lot of analogies, even though Jupiter is a little bit bigger, whatever. And the Jovian and Saturnian systems are very different, right? The Jovian system is dominated by these 4 giant moons. They do giant moon things. Yeah. It all kind of makes sense. And then you look at Saturn and there's like Titan, and then there's like this giant ring system. There's a whole bunch of like, what is Hyperion doing? Like Mimas is like, every moon is just kind of like, what happened here? And so somebody, Doug Hamilton, who, like, I don't know, 15 years ago or something, gave this talk. It was like Titan so big, so alone. And his premise was basically that it does not make sense for Saturn to only have one large moon. Like, if you try to just kind of form things, like, you expect it to form more large moons. And so his idea was like, okay, well, what happens if there used to be more large moons? And at some point they all smashed into each other and they made Titan. So he called them Titanos. And in his models...
Tholin's is better.
I know. I mean, we can just... we should, we need a linguist. We should not be left to our own devices, clearly. Yeah. So then the idea is basically there were a bunch of large moons. At some point, stuff happened. They smushed into each other. If you want to get real conspiracy theory, you potentially have the ability to explain the rings, weird things about Titan, Mimas, Hyperion, like all the mid-sized moons with their weird orbital elements, like Titan should be on a completely like spherical orbit or circular orbit. It's not. Its orbit is elliptical, which it shouldn't be. And also, and this is where the Titan people kind of are like, well, we don't hate your idea. Something massive, global scale, big deal, we're pretty sure happened on Titan around 700 million years ago.
How do you know?
Yeah. And actually, I think the more recent data even say maybe like 300, so like 300 to 700 million years ago.
God, it's all very recent.
Yeah, it's annoying. It's like, no, this is not how I was trained to be a planetary scientist. So it comes from looking at things like how old the surface is, from crater counting, from evolution models. Titan's surface is very young. It's undergoing a bunch of erosional stuff. So you're like, okay, cool, whatever, sure, Sarah. Yeah. But then when you do the math, you're like, no, really? We have done atmospheric evolution models looking at isotopes from Cassini data. There are interior evolution models that kind of say, okay, well, if this does this and this does that, we have like massive methane outgassing at some point. Like, there's, I would say, kind of 10-ish pretty independent lines of evidence that all point to something really catastrophic happening somewhere in the last billion years. And when you ask all of those people, like, would it be okay if Titan is only 1 billion years old? Everybody's like, well, it feels kind of itchy, but like scientifically I would be okay with it.
Sure. Okay.
So,
feels kind of itchy as an interesting statement. Yeah, where it's like something catastrophic happened here a billion years ago, and it's like the moon starting to exist.
But I remember the first time he talked to an all-Titan conference about this idea, and he finished and like every hand shot up. And he answered questions.
They're like, I have something to add to this.
Well, he answered questions, we talked to each other, and at the end, everyone kind of sat down and was like, well, I guess. I mean, if that explains it, and like, it would be such an elegant solution to all of the things that are weird about the Saturn system. Like, that part of your science brain is like, ooh, we do love us an elegant solution. I don't know if we love us Titan being like 500 million years old.
Yeah, I mean, look, we weren't around. We don't know. The thing is, and this is so true of like everything we know about things off of Earth, we know so much based on so little. Mm-hmm. It's amazing. Yeah. Like the fact that we know how far away other things are. Like, think about it. You couldn't figure that out. It took a lot of people figuring out a lot of different things to put that all together. But a little bit, where Titan comes from, I'm honestly less interested than like, oh, so we've got an entire chemistry lab doing, I know people think chemistry is boring and I need to fight this. But like, we got this entire thing going on and we do not know what happens in circumstances like this. There's just like, we can't, like, you think that it's just physics and it is, but it's so weird. It gets so strange so fast. Correct me if I'm wrong. Do we not really know what the surface of Titan is? Like, we're going to go down there and figure out if it's ice or tholin or sand or like, we're not sure.
Yeah, we don't.
Or ice is kind of sand on Titan because it's just a rock.
Well, we know that the sand grains in the dune fields, which are kind of one of the main geologic features on Titan from the mid-latitudes in the south to the mid-latitudes in the north, we know that we know they're not silicate sand. So they're not sand the way that you and I or Mars or Venus or Earth think of sand. We also know that they are not pure water ice.
Okay.
So we think that they're made out of organics or some mix of organics and water ice. Material that was made in the atmosphere ended up on the surface. But you're right, we don't know what the surface is made out of. We also, even making educated guesses about that, don't necessarily have great data about what water ice is like at 94 Kelvin. And so one of the really big challenges with sending a surface mission to Titan is not knowing what the surface is made out of, right? Like, we're carrying a drill that has to be able to drill into basically anything because we don't know what the surface is made out of. And so, like, this is, not just a scientifically challenging mission, but in terms of engineering challenges, this isn't, not to bash Mars, but like, we're not sending a mission to a place that we're used to. And that has been one of the things that I think has been really, I think our engineers enjoy the challenge because they get to like exercise their skills and their brains. But I assume every once in a while they're like, couldn't we just go to Mars?
Right. Well, there's this great thing about Titan where the gravity is very low and the atmosphere is very thick. So it's easy to fly around. So there's that. You got that going on Mars. But what you don't have is like knowing what's going on at all. And also you have a much more hostile environment. Generally, I would think, these particulates, who knows what they are or what they're going to do to the parts of a machine.
Yes.
And then in addition to that, it's very cold. Yeah. It's just very cold.
Yes, I think that's an understatement.
So being able to sort of say like, I think that we could fly a mission to Titan and then have the mission fly around in the atmosphere of Titan is pretty nuts. But they said yes. And then maybe they said no a little bit, but then they said yes again. How has that felt as being part of the this thing needs to happen and it costs money thing?
So backing up one step, Dragonfly is part of the New Frontiers program for NASA. Everyone knows and loves New Frontiers missions. OSIRIS-REx, New Horizons, Juno, like we know them, they're our friends. We have a list of targets that we know ahead of time that we propose these missions to. And when NASA released the list of targets for this particular New Frontiers call, out of nowhere, it added Titan and Enceladus. So most of the missions that were proposed to this New Frontiers call, people had been working on for years and years and years and years. Many of them had been proposed before in other forms. And then the Titan and Enceladus community just kind of were like, oh shit, what do we do? And so it was just kind of like 0 to 60 in 10 seconds. Like if we're going to do this, the idea has to exist right now. We have to start right now. And so there was initially a very small group of people who got together at the Applied Physics Laboratory who are leading the mission. They kind of were like, what can we propose to Titan? A couple of people were like, hey, so like I have this crazy idea. And by the time I got involved, the PI of the mission, Zibby Turtle, emailed me and she kind of said, some folks at APL have been bouncing around some ideas about a Titan mission. Like, would you be interested? And I have a screenshot of the email saved now because I basically replied to her, if it's Titan, I'm in. Later on, as they started kind of amassing the science team, because I'm local, they had me come down and basically, without ever telling me what the mission was, I sat through an entire presentation about it. And Zibby and her husband, Ralph Lorenz, who is our mission architect on Dragonfly, turned around and Ralph says to me, "So do you think we're crazy?" And I kind of wanted to be like, is that even the right question? Like, let's do it. Like, because I'm not an engineer. If the engineers say that we can do this,
what do I know?
I'm in. Like,
it's like so you're telling me you're gonna put a mass spec on Titan? I'm there.
Yeah, exactly.
Like,
I mean, it's literally like my entire career life dreams. Like, you're telling me that you have a plan for making my life's dreams come true. Like, yes, okay, let's do it. We're in. And having been there from that early on has been such a huge privilege. It's the most amazing team you could possibly imagine. I mean, this has been from the very beginning until today, just the absolute biggest honor of my life. These are the smartest, hardest working, most caring people I have ever had the privilege to work with. They are all so excited about the mission, but they're also equally excited about making sure that the entire community and all of humankind has the opportunity to participate as we start to get our data coming down and all of this. But I just think the public thinks it's so cool, right? Like, we're going to send this flying spacecraft to Titan, and it's really cold, and we're going to do mass spec measurements, we're going to get cool pictures, and we've got a drill, and I'm just so excited for everyone to be able to come along with us. And we have now been working on this mission for 10 years. We're 2 years from launch, and it's just oh, this is really happening. 45 minutes from here, there is a clean room with a spacecraft getting assembled in it.
Have you seen it yet?
I have. I've been down there a couple times. I was down there, I think about a month ago was the last time I was there. When I was hired at Hopkins 12 years ago, I went and did a tour at APL as they were trying to recruit me. And I remember the person giving the tour kind of dragging me to spacecraft assembly and kind of just projecting and someday they will build you your space robot here. I can't go down there without crying. I might start crying now, but anytime I go there and I stand in front of spacecraft assembly, I'm there it is. There's my, and it's not my space robot.
No, you did it all by yourself.
The space robot of many people, but it's so cool watching it get assembled, the care that people put into it, but also just it was an idea on a napkin, and then it was 150 billion Zoom meetings, and now it's a thing that people are using wrenches and
that's what planetary scientists do. You turn Zoom calls into spacecraft, and it's wonderful. Thank you for doing that. Zoom calls and PowerPoint presentations and
so many emails
and stressfully staring at the ceiling. So thank you for doing that.
Well, you're welcome.
Let's end on life again. We generally talk about missions as if they are sort of we're more looking at habitability. Sometimes we actually say we're going to try and figure out if there's life here, but usually we're not there yet, and so we're going to be to go and think oh, would this be a habitable place? But Titan, unless we're talking about a subsurface ocean, not traditionally habitable. Can I ask, because it doesn't seem to be a closed door to you anyway. It seems like you think that there might, the chemistry is weird and can do weird things. Do you have mechanistic ideas? I don't see, as with the limited amount of exochemistry, exobiology I've got, I don't see a methane lake being a great solvent for cool chemistry to happen. But air is also a fluid. I don't know. There's do you think about that?
Yeah, I mean, I don't. Again, I tend to be on the earlier side of this question than a lot of the exobiology people. So mechanistic stuff, I tend to leave a little bit more to my other colleagues. I think that we have a very Earth-centric idea of what life requires. And
also what life is.
And what life is, and what is favorable for life, and what conditions lead to life, and all of those things. The main thing that I have taken away from Earth life, as being a participant in it on most days, is that once life got a foothold on Earth, it was able, through evolutionary processes, to take advantage of every source of energy, every source of food, every source of shelter, every, water. Life, once it got going, was able to use everything that was available to it. I think that is probably something that I would consider to be fairly fundamental to life, for better or for worse. Right now we're seeing the consequences of the for worse. But
it grows until it can't anymore. The thing that natural selection selects for is making more of yourself.
Right. So for me, Titan, as far as we understand it, the very biggest picture you can possibly imagine, has energy. It has organics everywhere. It has liquids, multiple liquids, and it has had time, maybe not as much time as we thought originally, but it's had time.
Still a lot.
And so to me, it has had the opportunity. Whether that opportunity resulted in life or not, I think comes down to a really fundamental question of how ubiquitous life is. And I'm not, the longer I do this, I feel like I become increasingly less convinced that life is ubiquitous. I am increasingly more suspicious that life requires a very rare event to occur. It mildly terrifies me once in a while that maybe the event has only occurred once. I don't like that idea at all. But there's a bunch of places in the solar system that really have all the stuff as far as we understand the stuff, and they don't seem to have done much with it.
Well, I mean, we don't know. We don't know what the inside of Enceladus is like. We don't know what Europe is like in there.
Well, we do know that there are not skyscrapers. There are not.
Yeah, no, I think it would be
centers,
really.
There are not swimming pools.
There's a really. This is more where I'm at, and now we're chatting. But this is more where I'm at. I think that life may be fairly common, but that the systems necessary for that life to, like, one, for there to be stability long enough for, like, multicellularity and then backbones and all the weird, stuff that has happened over the last 4 billion years on Earth, that stability might be rare. And then in addition to that, there might be a lot of, like, intermediate conditions that are, like, if all of Earth life had happened inside of Enceladus, I don't think it ever would have gotten through the ice sheet. Like, I don't think that we would have figured out that there was anything above the ice sheet. We just think that that's the end of the universe.
Yeah, maybe. There's a bunch of little shrimp that on Enceladus that are like, and that's where everything ends, you guys. And they sit there with their little shrimp children telling their little bedtime stories about how the whole thing, the end of the universe is.
Like one day someone was like, I figured it out. The Earth is round, except the inverse of the way that our Earth is round.
Except
they're like, there's a round inside, and then there's a round outside, and that's the shape of the universe. And that's just what they'd think. Like, it's very, like, you can't imagine going through it.
I mean, and then every once in a while, one of the Enceladus shrimp gets shot out of plume and manages to come
out,
but then it comes back down, and then it tries to tell everybody stories, and they think that it's lost.
And it's like, ha 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 ha.
Yeah, I don't know.
Conspiracies.
I will say, since we're talking about this, that I am contractually obligated to say the Dragonfly is not a life detection mission.
Correct.
But we are equipped.
Do it anyway.
we're equipped should life exist. There are a number of ways in which we would hopefully see the signal of that in our data, despite not being a life detection mission. And so we are.
Can you see isomers?
So the mass spectrometer has a chiral column. So if we see amino acids and there's enough of them, we should be able to look at chirality. We have gone into it with the idea that whatever it is that we see, we want to be able to characterize as much as possible.
Yeah.
And that will provide us with infinite information about life or not life.
So much more information than we currently have. And for people who don't, we just used a bunch of terminology. Life picks a handedness. Life on Earth prefers one way of chemistry happening, and in terms of because two hands are not actually, they're
different.
It turns out they're different from each other. They're the same. They're the same, but they're different. And in non-living systems, you get equal amounts of both, and in living systems, you get one being preferred. So if you can detect that in the plume of an ice volcano in space, or in the sands of the dudes of Titan, then you'd be like, well, that's real weird. It's hard to explain that another way than some kind of self-replicating system. Sarah Hörst, thank you so much for doing your work and for spending a little bit of time with me. And I was just so pleased that I can get it. I was able to get in touch with you to have this chat.
Thank you for having me, and also just thank you for being excited about Dragonfly. I'm so excited. When you're deep in it, you think it's just the greatest thing that has ever happened, and it's it's very reassuring to hear that other people also are excited about it, because it's a lot of work, and it's nice to know that people are already excited. We've still got 8 years until we get there, but
yeah,
they're gonna fly by.
2 years to launch, but then we don't have infinite jet fuel, so you gotta. I mean, I guess rocket fuel is the correct term. So
I'm not that kind of scientist.
Exactly. You got to take your time. Use gravitational assists and stuff.
Yep.
And all those middle schoolers who are currently in middle school and will be studying the data in your lab as postdocs, that'll be amazing. Thank you.
You're welcome.
Was that into the worst possible way to end the interview? Thank you for watching all the way to the end. Now it's time, if you would like to get your Saturn Moon shirt designed by Casey Wachowski, you can get that now. It's a pre-order for the next 2 weeks and then no longer available. Also, let me know if anybody still wants the Jupiter Moon shirt. We might be able to do a quick little run of that one as well. It's beautiful, and I love Saturn, and I love Titan, and thank you so much to Dr. Hörst for having a chat with me, and thank you to you for watching all the way through.